is chapter 6.2, and you guys are going to apply properties of rational exponents. So you need to make sure that you remember the properties of exponents from chapter 5 in your book. And these are all the properties that we did at the beginning of chapter 5. So you should have those in your 5.1 notes, or they're in page 330 in your textbook. And then there's also examples of these properties, but with rational exponents. So a fraction on page 420 in your textbook. We need to make sure we remember the product property and the quotient property. So the product property says that if you have something under the radical, you can split it up into its two factors that are being multiplied. And then the quotient property says if you have division underneath the radicals, you can split it up into a radical in the numerator and the denominator. And we'll be doing both of those too. All right, so first we're just going to use the properties of exponents, and we're going to be looking for if they have the same bases or the same exponents. So in the first one, we notice that both of the bases are 8. So our properties of exponents say that if the bases are the same, we're just going to add the exponents. So we're going to have 8 to the 1/4 plus 2/5 power, which if you find a common denominator and add them, or you can add them in your calculator, you're going to get 8 to the 13/20 power. You don't have to write this middle step. You can just do this in your head or in your calculator, and this would be your final answer. All right, in example 2, notice that the exponents are the same. So we can actually take these out of the exponent spot and rewrite it as 20/5 to the 1/2 power, which is all to the 3rd power. So we're kind of doing the power of quotient rule, but we're doing it backwards, where we're taking this exponent outside of the parentheses. Then that allows me to simplify 20/5, which is just 4 to the 1/2, all cubed. We learned yesterday in 6.1 that anything to the 1/2 power can be rewritten as the square root. So that's the square root of 4 cubed. We know the square root of 4 is 2, and 2 cubed is 8. So 8 would be your final simplified answer. On this last one, notice that the bases aren't the same and neither are the exponents. So what we're going to do first is raise each exponent to the 2nd power. And when we do a power to a power, we multiply. So we've got 6 to the 1/2 squared times 4 to the 1/3 squared. 1/2 times 2 is just 1, so we're just left with 6. And we've got 1/3 times 2, which is 2/3. There's nothing else I can do here because the bases are not the same and neither of the exponents, so that's as simplified as that's going to get. All right, next we need to look at simplifying the radical when the index isn't 2. Mostly everything we've focused on in class has been square roots, and sometimes we've looked at cube roots, but we also need to know how to simplify when the index is bigger than 4. So one way to go about simplifying these is to make a factor tree. And when you do the factor tree, you are looking for groups that are equal to the index. So I'm going to make a factor tree just like I would normally if I'm doing simplifying a square root. But instead of looking for groups of 2s, now we're going to look at groups for 3 numbers that are the same. So you can split 135 into 5 and 27. 7 can be split into 3 and 9, and 3 and 3. Notice that I have 3 3s. That group of 3 comes out front, and I'm doing 3 because that's the number that I have 3 times. 5 is left over, So that's going to stay underneath your radical. So the cube root of 135 simplifies to 3 times the cube root of 5. You can also think of the product property. If you know a factor of 135 is a cube root, I could rewrite this as the cube root of 27 times the cube root of 5 because of my product property. The cube root of 27 is 3, and you're just left with the cube root of 5. So you get the same answer, and you can do it either way. Either make a factor tree or use the product property. If you're doing the fourth root of 240, again, you can make a factor tree, and you're looking for groups of 4 numbers that are alike. So you could split this into maybe 5 and 48, and you can pick any 2 factors that you want to start with. You could do 2 and 24, 2 and 12, 2 and 6, and 2 and 3. So notice I have 1, 2, 3, 4 2's, and I'm looking for groups of 4 because that's my index. So 2 is going to go on the outside. You're left with the fourth root, and we have a 5 and a 3 left over. Those get multiplied and put back under. If you knew a factor of 240 that was you could take the fourth root and get a perfect number, you could rewrite that as the fourth root of 16 times the fourth root of 15. The fourth root of 16 is 2, and you're left with the fourth root of 15. So again, you get the same answer. 1, you're making a factor tree. 1, you're doing the product property. All right, now we're going to look at rationalizing the denominator. We have done this only with square roots. It's going to be a similar process, and I want to show you why it works. So let's remember rationalizing the denominator. Let's say we have something like 2 over the square root of 2. We rationalize the denominator when we have a square root in the denominator. We say that it's not proper to leave it that way, so we rationalize it by getting rid of the radical. The way we do this is we multiply by that radical top and bottom, because that's 1. And when you multiply fractions, you multiply straight across. So you have 2 radical 2. In the denominator, let's think about this being rewritten with rational exponents. So the square root of 2 is 2 to the 1/2. When I'm multiplying these, I'm adding the exponents. So I end up with 1/2 plus 1/2, which is just 1. That's why the radical goes away, because these exponents are adding to 1, so I'm just left with 2. And then, of course, you can simplify those, and you're just left with the square root of 2. Now, if we're doing this when the index is not 2, I recognize that it needs to be rationalized because this radical is in the denominator, and I can't simplify the fourth root of 27. So what you're going to do is rewrite the numerator, and you're going to try to rewrite the denominator so that the radicand has a base raised to some exponent. I can rewrite 27 as 3 cubed. Those are equivalent. All I did was rewrite it as 3 cubed. Now, the only difference between this and the last example we did, we're still going to multiply it by a number on the top and the bottom, but it's not just going to be what we see in the denominator. It's going to be the fourth root, because that's what the index is, but you have to choose what exponent you want so that when you add these, they add to be the same as the index. The base is going to stay the same. So here I'm going to multiply by the fourth root of 3. On the bottom, if I'm multiplying, I'm adding the exponents. So product property, the fourth root stays the same, and I add the exponents. 3 plus 1 is 4. The fourth root of 3 to the fourth is just 3. So we've gotten rid of the radical. Now up top, since the indices are the same, you can just multiply what's underneath. So you've got the fourth root of 10 times 3 is 30. And you can leave it just like that, the fourth root of 30 over 3. So again, we took this radicand and we rewrote it as a base to some power. You choose what this exponent's going to be so that when you add them, they equal the index. The radical is going to stay the same, the base is going to stay the same. You're just choosing what you want the exponent to be. So let's try this one. The sixth root of 7/4. We need to rewrite this with our quotient property. So the sixth root of 7 over the sixth root of 4. Now 4 can be rewritten as 2 squared. Now when we multiply, it's going to be the sixth root of 2 over the sixth root of 2, and I have to choose what this exponent's going to be, so when I add the exponents, they equal the index. So 2 plus 4 is going to give me 6, so that's what's going to go there. Here, when I multiply in the denominator, the radical stays the same, and I multiply what's underneath. These are the same, so I add the exponents. I have the sixth root of 2 to the 6th, which is just 2. Now up top, I need to multiply 7 times 2 to the 4th. So 2 to the 4th is 16, times 7 is 112. So we have the sixth root of 112, and you can leave it just like that. All right, the last couple we're going to look at, we are adding and subtracting radicals and roots. When you do this, the radicals have to have the same index, and the radicand, what's underneath, has to be the same for you to be able to add or subtract. So on this first one, notice they're both the fifth root of 12, so we're just going to subtract the coefficients. The coefficient of this is 1 since nothing's written there. So it's like we have 7 minus 1, that's 6. And you can think of the fifth root of 12 like your variable. So that's that simplified. Just subtract the coefficient. 7 minus 1 gives you 6. Now on this one, notice they are not the same. So you need to try to simplify them so that they are. So if I'm going to simplify the fourth root of 1250, I can make a factor tree. That splits into 50 and 25. That splits into 2 and 25, 5 and 5, 5 and 5. So notice I have 4 5s, and I'm looking for groups of 4 because that's the index. So I'm going to leave the 2 there that was there. I'm simplifying the fourth root of 1250, and that's 5 fourth roots of 2 because 2 is what's left. Minus 8, that's the 8 to begin with, and now I need to simplify this. 32 can be split into 2 and 16, 4 and 4, 2 and 2, and 2 and 2. 4 2s, so a 2 comes out, and I've got a 2 left over, fourth root of 2. Now let's simplify what we have so far. 2 times 5 is 10 fourth roots of 2. Minus 8 times 2 is 16 fourth roots of 2. Now that those are equivalent, all I have to do is 10 minus 6, and I've got negative 6 fourth roots of 2. So if they're not the same, make them the same by simplifying, and then just add or subtract the coefficients depending on the sign. All right, our very last examples have to do with simplifying, but with variables now. When you do these, all the same rules apply. Now we're just using a variable instead of a number. On the first one, we're taking the fourth root of 12 times x squared times y to the sixth times z to the 12th. So really, you're taking the fourth root of each term individually. If you want to rewrite it out like that, that might be helpful. And if not, you can leave it just like it is. Now, the fourth root of 12. Let's do some work off to the side. If I try to simplify that with a factor tree, this is what I get. There are no groups of 4 that go into that, and it has to be a group of 4 because that's the index. So I can't simplify 12. So I'm going to leave the fourth root of 12 there. Now I've got the fourth root of x squared. X squared is just x times x. So there's not 4 groups of anything there, so x squared has to stay. Y to the sixth, that's y times y times y times y times y times y. 1, 2, 3, 4, 5, 6. If you multiplied all of those, you would get y to the sixth. I'm looking for a group of 4. I have one group. So I can take a y out, and I'm left with y times y, so I'm left with a y squared underneath. The last one is the fourth root of z to the 12th. Now let's think about this instead of writing it out. Z to the 12th is z 12 times. There are 3 groups of 4 in there, because 12 divided by 4 is 3. So you're going to take out a z cubed. So that means there's no z's left. So this would be your final answer. Z cubed times y times the fourth root of 12 x squared y squared. Let's look at this one. The cubed root of 27 times q to the 9th. So again, let's apply this radical individually to each term. The cubed root of 27 is 3. We're looking for the cubed root of q to the 9th. You can divide these. 9 divided by 3 is 3 evenly, so we're just left with q cubed. So this simplifies to be 3q cubed. You can check your work. If you were to cube both of these things, you should get back here. 3 cubed is 27. Q cubed to the third power is q to the 9th. Okay, I'm going to skip down to this one. Here we're subtracting. In order to subtract, what's underneath the radical has to be the same. So I'm going to see if I could simplify either one of these. Let's start with the first one. The square root of 9, that's 3. The square root of w to the 5th. Write it out if you need to. W to the 5th is w multiplied by itself 5 times. We're looking for groups of 2 because that's the index. There's 2 groups of 2 w's. So we're going to multiply w times w. W squared is going to come out, and this leftover w has to stay underneath. Minus w. The square root of w cubed. W cubed is w 3 times. There's one group of 2 in there, so a w comes out, and there's a leftover w. So let's simplify what we have. 3w squared times the square root of w. W times w is w squared times the square root of w. Now, these are the same, so I just subtract what's in front. 3w squared minus w squared is 2w squared times the square root of w. All right, so we will practice more of these tomorrow, and make sure you come to class with the code word, and the code word today is Jayhawk.